Hello there, and welcome to Sleepy Science Vault. The universe is, for the most part, empty. Not empty in the way a room feels empty when someone has just left it, but empty in a deeper, more absolute sense. Empty in a way that is difficult for the human mind to hold on to for very long, because everything we know, every mountain, every ocean, every star we can see with our own eyes, exists inside the tiny fraction of space that is not empty. Tonight, we are going to drift into that emptiness. We're going to explore the loneliest places in the universe, the vast, quiet, underpopulated regions that make up most of everything that exists. And we're going to move through them slowly, the way light itself moves through them, patiently, without hurry, across distances so large that human timescales barely apply. This is a journey meant for slow listening. For a mind that's ready to unwind. For a night where you'd rather drift than concentrate. So let the facts come to you gently. There's no need to hold on to every detail. Just let the scale of things wash over you, the way it should. Let's begin where the universe itself begins to feel truly vast, in the cosmic voids. Cosmic voids are enormous regions of space that contain very few galaxies. When astronomers describe a region of the universe as a void, they don't mean that it contains absolutely nothing, but they do mean that, compared to the rest of the universe, it is startlingly, almost unnervingly empty. Imagine standing in the middle of a desert so large that the nearest town is not miles away, but hundreds of millions of light years away. That is the kind of isolation we're talking about. Regions where galaxies, those vast cities of stars we usually think of as scattered everywhere, become rare. Sparse. Almost accidental. These are, by simple measurement, some of the emptiest places known to exist anywhere. And yet, it's worth pausing here, gently, on something important. The loneliness of these regions is not loneliness in the way we feel it. It's not emotional. It's not a void reaching out and yearning for company the way a person might on a quiet night. When scientists use the word lonely to describe these regions, they are speaking in the language of measurement, not feeling. A cosmic void is lonely only in the sense that very little exists there to keep it company, not because it experiences its own emptiness. This distinction matters, because it's easy, especially late at night, especially when the mind starts to wander into poetry, to imagine these voids as somehow aware of their own vast solitude. But the universe doesn't feel that way. Emptiness, out there, is simply a fact of geometry. A fact of density. Nothing more, and yet, somehow, nothing less profound for it. Still, there is something moving about it. Something quietly beautiful. To know that such enormous stretches of existence pass by without a single galaxy to interrupt them, without a single star to cast light across the dark, and that this vast, undisturbed silence is simply how so much of the universe naturally is. Not sad. Not empty in the human sense. Just vast. Still. Undisturbed. These regions are not just empty in the way a random gap might be empty. They are among the most isolated, least dynamic environments that astronomers have ever observed. Dynamic is an interesting word here, because it hints at something deeper than simple emptiness. In a busy region of the universe, where galaxies cluster together, colliding, merging, pulling at each other with gravity, there is constant change. Motion. Interaction. Galaxies bump shoulders with their neighbors. Gravity tugs them into new shapes. New stars form as gas clouds collapse under the pressure of nearby galactic activity. But in a void, very little of that happens. Without galaxies close together, without matter dense enough to interact meaningfully, these regions settle into a kind of profound cosmic stillness. Change comes slowly there, if it comes at all. Whole eons can pass with almost nothing happening. There's something almost meditative about that thought, isn't there? Regions of existence so vast, so old, where stillness itself has had billions of years to simply continue. Now, here is something that might surprise you. Even though cosmic voids contain remarkably little matter, they are actually the most prominent feature of the universe's large-scale structure. Let that settle for a moment. You might expect that when astronomers map out the shape of the universe, the important features would be the busy places, the galaxy clusters, the bright filaments of matter, the crowded neighborhoods where stars pile into galaxies and galaxies pile into groups. But it's not quite like that. When you zoom out far enough, far beyond individual galaxies, far beyond even galaxy clusters, the true shape of the universe reveals itself as something more like a sponge, or a web, or, as we'll return to shortly, something like a foam of soap bubbles. And within that structure, the empty spaces, the voids, are not just gaps left over after the real structure was built. They are, in a very real sense, part of the architecture itself. Structural. Defining. The negative space that gives the whole pattern its shape. Think of it like this: if you looked at a photograph of a lace curtain, you wouldn't say the holes in the lace are unimportant just because they're empty. The holes are what make the pattern recognizable as lace in the first place. Remove the empty spaces, and the pattern disappears entirely into a formless mass. The universe, on the very largest scales, is a little like that. The emptiness is not accidental. It's essential to the shape of everything. So what exactly are these voids, in more precise terms? Cosmic voids are defined as large underdense regions within the universe's large-scale structure. That word, underdense, is really the key to understanding them. It doesn't mean empty in an absolute sense. It means less dense than the surrounding universe. Less matter, less gravity, less gathering, compared to the regions around them. This is worth repeating gently, because it's such a central idea. Cosmic voids are large, underdense regions, within the universe's overall large-scale structure. Vast stretches where matter simply thinned out, long ago, and never thickened back up. To understand why that happened, it helps to zoom out and picture the universe not as a random scattering of galaxies, like sand thrown across a table, but as something far more organized. Far more architectural. Galaxies don't scatter evenly through space. If they did, the universe would look roughly the same no matter where you looked, a smooth, even mist of light spread out in every direction. But that is not what we observe. Instead, galaxies gather together. They form long, thread-like structures called filaments, vast bridges of galaxies stretching across unimaginable distances. These filaments connect to one another at dense knots, places where galaxy clusters gather in huge numbers. And between those filaments, spreading out in flatter formations, are structures called walls, sheets of galaxies stretched thin across space, like the walls of some enormous, cosmic structure. And in between all of this, between the filaments, between the walls, between the knots of galaxies, lie the voids. The emptied-out spaces. The quiet rooms of a universe otherwise humming faintly with galactic activity. This overall arrangement even has a name. Astronomers call it the cosmic web. And this is one of those facts that, once you hear it, is hard to unhear. The cosmic web is considered the largest known pattern in all of nature. Not just the largest pattern in the universe as astronomers study it, but the largest organized structure of any kind that we know of, at any scale, made of anything. Larger than any pattern in biology. Larger than any structure in geology. Larger than anything humanity has ever built or imagined building. A pattern so vast that its individual threads, the filaments of galaxies, can stretch across hundreds of millions of light years. And the voids are the spaces between those threads, the gaps between the strands of the largest web nature has ever woven. It's worth sitting with that image for a moment. A web spun not from silk, but from galaxies. Threads made of light. And spaces between those threads so enormous that entire other patterns, clusters, superclusters, filaments, could be lost within them and still leave room to spare. Now, it might be tempting, hearing all of this, to think of voids as accidents. Leftover gaps. Empty spaces that just happened to end up empty because nothing filled them in. But that's not really accurate, and it's worth being gentle but clear about this. Cosmic voids are not simply random gaps in the universe. They are a fundamental part of its large-scale structure, just as essential to the shape of the cosmos as the filaments and walls that surround them. In other words, the universe didn't accidentally leave these spaces empty the way a puzzle might accidentally have missing pieces. The emptiness itself is a natural, expected outcome of how matter organized itself in the earliest ages of the universe. How gravity pulled some regions together while letting others drift apart, thinning out over billions of years until they became the vast, still spaces we observe today. The emptiness had to exist, in some sense, for the fullness to exist at all. You cannot have a web without gaps between its strands. You cannot have structure without spaces that structure defines by not filling them. There's something quietly comforting in that idea, if you let it settle slowly, that even the emptiest places have a role. A purpose within the pattern. Not filler. Not accident. Simply, part of the design. So how do astronomers actually picture this pattern, when trying to describe it to people who aren't used to thinking on cosmic scales? One of the most common comparisons, and one of the most strangely calming ones, if you let your mind sit with it, is soap bubbles. Picture a sink full of soapy water, right after you've done the dishes. If you look closely at the foam sitting on the surface, you'll notice something interesting. The bubbles themselves are mostly empty air, wrapped in a thin film of soap. But where multiple bubbles touch each other, the soap film thickens, forming walls, And where several of those walls meet, you get denser junctions, points where multiple bubbles' edges converge. Now, replace bubbles with cosmic voids. Replace soap film with galaxies. And you have, in miniature, a strange little echo of the largest structure in the universe. The galaxies gather along the thin films, the walls and filaments of the cosmic web, while the interiors of the bubbles, the voids themselves, remain almost entirely empty. Just as a soap bubbles inside is mostly air, a cosmic void is mostly nothing. Or at least, nothing compared to the crowded walls that surround it. It's a strange comfort, isn't it, to think that the largest pattern in the universe echoes something as small, as ordinary, as a sink full of dishwater. The universe, on its grandest scale, structured a little like foam. Fragile seeming, and yet stretched across distances that make fragile feel like entirely the wrong word. Let yourself sit in that image for a while, if you'd like. Soap bubbles the size of hundreds of millions of light years, their thin walls made of galaxies instead of soap, their insides holding nothing but quiet, ancient dark. As we drift further into this exploration together, over the segments ahead, we're going to travel deeper into specific voids. We'll meet places with their own names, their own recorded sizes, their own stories of discovery, regions of space so profoundly empty that astronomers have spent decades trying to understand why they exist exactly where they do, and why the universe allowed them to become so vast, so quiet, so still. But for now, let this first, gentle understanding settle over you like a blanket. The universe is not evenly full. It gathers itself into threads and walls, and it leaves enormous, quiet rooms in between, rooms that are not empty by accident, but empty by nature. Rooms that make up most of the true shape of everything that exists. And somewhere among that vast structure, tucked between the walls of the deep, we are here, in one small corner of one small galaxy, looking outward into the dark, trying, gently, to understand it. Let's continue drifting outward from here, into the specific voids themselves, into their names, their discoveries, and the strange, still worlds they contain. If you were able to step back far enough, far beyond galaxies, far beyond clusters, far beyond even the great filaments of the cosmic web, and taken the universe as one single, unified shape, you would notice something remarkable almost immediately. Most of it is void. Not most of its mass. Not most of its light. But most of its volume, the actual three-dimensional space the universe occupies, is made up of these enormous, quiet, underdense regions we've been exploring. It's a strange thing to picture. When we imagine the universe, we tend to picture galaxies. Swirling spirals of stars, bright clusters, glowing nebulae, the visual highlights, in a sense. But if you were to measure the actual space those things occupy, compared to the space that surrounds them, the galaxies would turn out to be almost incidental. Small bright specks scattered through an overwhelming, dominant emptiness. Voids make up most of the volume of the observable universe. Even though they contain very little matter, they claim most of the actual room. And according to some estimates, that most is a very large majority indeed. Some sources suggest that voids account for roughly 80% of the known universe's volume. 80%. let that number sit for a moment, because it reshapes the whole picture rather significantly. It means that if you were to close your eyes and randomly place yourself anywhere within the observable universe, not on Earth, not near any star, just randomly, anywhere within all that vastness, the overwhelming likelihood is that you would find yourself in one of these vast, quiet voids, surrounded by darkness, far from any galaxy, far from any light. Our own presence, here on Earth, in a busy spiral galaxy, surrounded by hundreds of billions of other stars, is not the typical experience of being somewhere in the universe. It is, statistically, the unusual case, the exception. Most of the universe's volume offers nothing like the crowded neighborhood we call home. That's worth sitting with gently. We live in a rare pocket of relative business, in a universe that is, by volume, overwhelmingly still. So what would it actually be like, in that stillness? The space between galaxy clusters is considered among the quietest, least active regions known anywhere in the universe. Quiet not in the way a library is quiet, with the occasional turned page or hushed whisper, but quiet in almost every sense that matters on a cosmic scale. No nearby stars to shine light across the dark. No nebulae collapsing to form new suns. No galaxies drifting close enough to tug at each other with gravity, sparking bursts of star formation the way crowded galaxies often do. Just darkness, extending outward for distances the mind struggles to hold on to, undisturbed by almost anything at all. If you could stand in the middle of one of these regions, and of course, no one ever has, or ever likely will, the sky around you would be almost entirely black. Not black with a scattering of faint stars, the way our night sky looks even in the darkest wilderness on Earth, but black in nearly every direction. The occasional distant smear of galactic light, achingly far away, would be the only interruption in an otherwise complete and total dark. It's an image that some people find unsettling, and others find strangely peaceful. Perhaps it depends on the night, and the mind that's imagining it. There's something else about these distant, quiet places that adds an even stranger layer to their isolation, something that goes beyond mere distance. The universe, as you may already know, is expanding. Space itself is stretching, gradually pulling galaxies away from one another as time goes on. And for regions far enough away, this stretching becomes so significant that something remarkable happens. Some distant regions are so far away that the ongoing expansion of the universe carries them beyond the reach of any light they emit. In other words, no matter how much time passes, no matter how patiently we wait, light from those regions will never arrive here. The space between us and them is growing faster than light itself can cross it. Take a moment with that thought, because it's a genuinely strange one, even by cosmic standards. Normally, we think of far away as simply meaning it will take longer for the light to reach us. Given enough time, a distant point of light should, eventually, become visible. But for these particular regions, no amount of waiting will ever be enough. The universe is expanding faster, in the space between us and them, than light is able to close that gap. This creates something astronomers sometimes describe with the idea of an horizon, not a horizon you could ever travel to and look beyond, but an horizon built into the very fabric of the universe itself. a permanent boundary between what we could, in principle, one day observe, and what has already slipped forever beyond our reach. There's a quiet strangeness to knowing that entire regions of existence, entire pockets of the universe, are, in a very real sense, already lost to us. Not destroyed. Not gone. Simply, permanently unreachable, no matter how far our technology advances, or how long humanity endures. Space itself decided the matter long ago. Now, let's return to something a little more tangible, at least in astronomical terms, the actual sizes of the voids we've been discussing. Some cosmic voids can span hundreds of millions of light years across. Let that phrase settle for a moment, because it's easy to say quickly, and much harder to actually absorb. A single light year, on its own, is already almost incomprehensibly large. The distance light travels in an entire year, moving at nearly 6 trillion miles every 12 months. And yet, some voids are so vast that describing their size in single light years wouldn't even be practical. Astronomers must speak in hundreds of millions of them, just to communicate how much empty space we're really talking about. The largest known voids extend for these hundreds of millions of light years in every direction, vast, roughly spherical regions, stretching out through space with almost nothing inside them to interrupt their emptiness. One of the most famous examples, one that even casual stargazers may have heard mentioned, is the Boötes Void. Some estimates describe the Boötes Void as being roughly 330 million light-years across. Try, gently, to picture that. Not to succeed entirely, no one truly succeeds at picturing a distance like that, but simply to lean toward it, the way you might lean towards sleep without quite arriving yet. If you were to travel outward from the center of the Boötes Void in any direction, moving at the speed of light itself, the fastest speed anything in the universe is permitted to travel, it would take you well over 100 million years just to reach its edge. And that's only half of its total span. Multiple human civilizations could rise, and fall, and be utterly forgotten, multiple times over, in the time it would take light to simply cross from one side of this void to the other. And that's just one void, among countless others scattered throughout the observable universe. Because astronomers work with distances so large, they often use a specialized unit to describe them more conveniently, something you may have heard mentioned before, called a megaparsec. A parsec, on its own, is already a substantial unit of distance, roughly equal to a little over 3 light years. A megaparsec is 1 million of those. And when astronomers describe the typical size of cosmic voids, they usually give their radius, not their full width, but the distance from their center out to their edge, in megaparsecs. Their typical radii fall somewhere between about 10 and 100 megaparsecs, in a unit astronomers write as MPC divided by h, a specific way of accounting for some of the small uncertainties in how quickly the universe is expanding. 10 to 100 megaparsecs of radius. Translated into light years, that range spans from roughly 30 million light years, on the smaller end, up to over 300 million light years, for the largest examples. A staggering range, and yet every void within it counts among the largest individual structures the universe contains. It's worth repeating, softly, because the scale is so easy to lose amid all the numbers. These typical radii, somewhere between 10 and 100 megaparsecs, describe regions so large that they rank among the biggest organized structures known to exist anywhere. Not the biggest pattern. We spoke earlier of the cosmic web claiming that title, but among the biggest individual, definable regions within that pattern. And this size range isn't a rare exception either. It's typical. Ordinary, even, by the strange standards of cosmic architecture. Void after void, scattered throughout the universe, each one spanning tens or even hundreds of megaparsecs, each one a quiet, dark room within the grand structure of everything. Somewhere out there, right now, light is failing to cross the distance of a single void, still traveling, still years, millions of years, away from reaching the other side. It has been traveling since long before Earth's oceans existed. It will still be traveling long after we are gone. And there is nothing hurried about its journey, nothing anxious in it. Just steady, patient motion, drifting through the dark, the way so much of the universe simply continues. We've spent this stretch of the journey understanding the scale of these places, how much space they occupy, how quiet they are, how some of their edges remain forever beyond what we could ever observe. In the segment ahead, we'll move even closer towards specific discoveries, specific findings, and the strange story of how humanity first noticed these vast empty rooms scattered throughout the sky. For now, let the scale settle over you gently, hundreds of millions of light years of stillness, stretching outward, patient and dark, forming most of the true shape of the universe we live in. By now, you have a growing sense of just how much of the universe is given over to emptiness. Radii of 10 to 100 megaparsecs, stretching across hundreds of millions of light years, claiming the overwhelming majority of the observable universe's volume. It's a scale that resists easy comprehension, no matter how many times you turn it over in your mind. So let's shift, gently, from the general to the specific. From the abstract mathematics of megaparsecs and volume percentages, towards something a little more grounded, the individual voids themselves, and the strange, quiet story of how we came to know they were there at all. We'll start small, in cosmic terms at least, because even the smallest voids are worth pausing on. The smallest cosmic voids measured are still about 20 million light-years across, on a single side. 20 million light-years. It's worth remembering that this is the small end of the scale, the modest, unremarkable examples that barely register as noteworthy compared to their larger cousins. And yet, if you tried to imagine crossing even one of these smaller voids, the number remains almost beyond grasp. 20 million years, traveling at the speed of light, just across from one side to the other. Long before that journey's midpoint, entire geological ages on Earth would have come and gone. 20 million years ago, distant ancestors of modern whales were still adapting to life in the sea. In that entire span of time, the whole slow unfolding of those 20 million years equals just the width of the smallest voids we know of. The large ones, as we've already discovered, dwarf this by an extraordinary margin. And among the large ones, one void in particular tends to come up again and again, in books, in documentaries, in the quiet corners of astronomy forums where people gather to marvel at the strange shape of the universe. The Boötes Void. Named for the constellation Boötes, in whose direction it appears when viewed from Earth, This void has earned a nickname that captures something almost poetic about its nature. Astronomers and science writers alike have taken to calling it the Great Nothing. The Great Nothing. There's something almost literary about that phrase, isn't there? Not clinical, not purely scientific, but evocative, in a way that suggests the scientists who study this region were themselves struck by something beyond mere data. A kind of quiet awe, translated into two simple words. The Boötes Void remains one of the most discussed examples of a cosmic void, and for good reason. It isn't simply large. It isn't simply empty. It's unusually large, and unusually sparse, even by the standards of voids in general, a region that stood out clearly enough, even in the early days of large-scale cosmic surveys, that it captured the imagination of an entire field of research. In fact, its size and emptiness are significant enough that astronomers place it in its own special category. The Boötes Void is often described as a supervoid, a term reserved for voids considerably larger than the typical, ordinary empty regions scattered throughout local space. A supervoid isn't just big. It's big enough to be considered exceptional even among a class of objects that are, by definition, already among the largest structures in the universe. It's the difference, perhaps, between an ordinary quiet room in a large house, and an entire empty wing, vast enough that its scale alone sets it apart from everything else nearby. This remarkable region was discovered in 1981, during a period when astronomers were first beginning to map the large-scale structure of the universe in serious detail. Prior to that era, our understanding of how galaxies were distributed through space was far less complete. Surveys were slowly, painstakingly cataloging galaxy positions, building up, point by point, a three-dimensional picture of where matter actually sat in the cosmos. And when that picture began to take shape around the region we now call the Boötes Void, something immediately looked unusual. A patch of sky where galaxies, which should have appeared scattered throughout in their typical numbers, were instead strikingly, almost eerily absent. To understand just how strange this find really was, consider the actual numbers involved. The Boötes Void contains only about 60 known galaxies, within a region of space where astronomers would normally expect to find several thousand. 60, instead of thousands. Try to sit with that contrast for a moment, because it's really quite staggering. Imagine expecting to find a bustling city, filled with thousands of buildings, thousands of lit windows, thousands of small signs of life and activity, and instead, arriving to find perhaps 60 scattered structures, spread thin across an area that should have held so very much more. It's a little like walking into what should be a crowded auditorium, expecting a packed house of thousands, and instead finding a handful of solitary occupants scattered so far apart across the seats that you'd have to shout, and even then, might not be heard. This dramatic scarcity is precisely why the Boötes Void captured so much scientific attention when it was first mapped, and why it continues to come up in discussions of cosmic structure even decades later. It isn't simply an empty patch of sky. It's an almost defiantly empty one, a region that seems to have missed out on the galaxy formation that shaped so much of the rest of the universe around it. And here, it's worth pausing to consider just how large some of these voids truly are, in terms that might feel a little more relatable. Some cosmic voids are so vast that entire galaxy clusters, enormous gravitationally bound groupings, each one containing hundreds or even thousands of individual galaxies, could be placed inside them, and still leave enormous, vast stretches of empty space remaining. Picture that for a moment. Take one of the largest, most crowded structures the universe has to offer, a galaxy cluster, humming with thousands of galaxies, rich with light and gravity and motion, and drop it into the middle of a supervoid like Boötes. It would sit there, a small island of activity, surrounded on all sides by distances so large that its own considerable size would barely register as a rounding error against the true scale of the void containing it. This is, perhaps, one of the most humbling comparisons available to us when trying to understand these regions. Even our grandest structures, the ones astronomers consider truly massive in their own right, become almost negligible when placed against the true scale of the emptiest places in the universe. And yet, despite everything we've said, despite the word void, despite the nickname Great Nothing, despite the almost complete absence of galaxies, it's important to hold on to one more gentle correction. These regions are not perfectly, absolutely empty. Cosmic voids do still contain some matter. Just far, far less than the average region of the universe. It would be more accurate to think of them not as regions of true nothingness, but as regions of profound scarcity, places where matter thinned out dramatically, but never vanished entirely. Within these vast, quiet spaces, you can still find occasional galaxies, like the 60 scattered throughout Boötes, faint and isolated, drifting through the emptiness with almost no neighbors to interact with. You can also find sparse structures of dark matter, that mysterious, invisible substance which makes up the majority of all matter in the universe, and which continues to exert its gravitational influence even in these underpopulated regions, shaping what little structure does exist within the void's boundaries. So perhaps the Great Nothing is, in the end, a slightly poetic exaggeration, not entirely accurate, but forgivable, given just how overwhelmingly empty these regions truly are compared to everything around them. Not nothing, but very, very close to it. Close enough that the difference barely matters, when measured against the fullness of the rest of the universe. There's something worth sitting with, in this final thought before we drift onward. Even in the emptiest places the universe has to offer, even in a region nicknamed for its nothingness, life, in some small form, still exists. Galaxies still burn, however faint, however far apart. Structure still lingers, however sparse. Even in the Great Nothing, something remains. Perhaps that's a small, quiet comfort, if you let it be one. That even in the vastest, loneliest reaches of existence, absolute nothingness seems difficult for the universe to fully achieve. Something, however faint, tends to remain. In the next part of our journey, we'll move even deeper into what fills these sparse spaces, the occasional galaxies that do exist within voids, and what they can tell us about the strange, isolated lives such galaxies must lead, adrift in the vast quiet, far from the crowded galactic neighborhoods most of their cousins call home. For now, let the Great Nothing settle over you slowly, 330 million light-years of near-total silence, holding within it just a handful of distant, solitary lights. We ended our last stretch of time together with a small, quiet thought that even the emptiest places the universe has to offer are rarely absolute. Something faint tends to linger. Let's follow that thread a little further now, deeper into the interiors of these vast, dark regions, to see exactly what that faint remainder looks like. It turns out that voids, for all their emptiness, are not simply smooth, featureless gaps in the fabric of space. Some of them contain faint internal structure of their own, scattered galaxies, as we've already learned, but also something more delicate and more surprising. Something astronomers have only really come to understand through careful computer modeling. Some voids contain what researchers describe as mini cosmic web-like filaments, small, faint echoes of the very structure that defines the boundaries around them. It's a curious thought, isn't it? The voids exist, in part, as the negative space between the great filaments and walls of the cosmic web. And yet, tucked within that negative space, tiny miniature versions of the same pattern sometimes appear, like a quiet echo repeating itself at a much smaller scale. This isn't something astronomers discovered simply by pointing telescopes at the sky, either. Voids are so sparse, so faint, that much of what we understand about their interior structure comes from computer simulations, vast digital models that recreate the gravitational behavior of matter across cosmic time, allowing researchers to watch, in simulated form, how structure forms and evolves across billions of years. These simulations reveal something that would be almost impossible to observe directly. Voids are not simply empty gaps sitting quietly in the dark. Within them, faint tendrils of dark matter drift and stretch, forming their own delicate, ghostly filaments, too faint, too sparse, too dim to ever be seen directly with a telescope, but present nonetheless, threading their way through the emptiness like the faintest suggestion of structure, barely holding on. It's a strange, delicate image, if you let yourself picture it. Not perfect nothingness, but something closer to a hush. A whisper of structure, present but almost silent, drifting through space where the loud, bright architecture of galaxies and clusters never fully took hold. And this faintness applies to more than just dark matter. It applies to everything. Both visible matter, the ordinary stuff of stars, galaxies, gas, and dust that we can actually observe with light-based instruments, and dark matter, that unseen substance which makes up so much of the universe's true mass, are scarce within these regions. Neither form of matter gathered in these spaces the way it did elsewhere. Both, in their own way, thinned out and drifted away, leaving these vast rooms comparatively empty of both the visible and the invisible alike. It's worth pausing on this point, because it clarifies something that might otherwise seem contradictory. You might wonder, hearing about dark matter filaments existing within voids, whether these regions are truly as empty as we've described. But the scarcity applies across the board. Whatever form matter takes, ordinary or dark, it exists here only sparsely, only faintly, only in traces compared to the fuller, richer regions that surround these quiet spaces. So how sparse, exactly, are we talking about? Astronomers have worked to quantify this rather precisely, and the numbers are worth sitting with for a moment. The matter density inside a typical void is often only about 10 to 50% of the universe's average density. In other words, if you compared the amount of matter packed into a given volume of space within a void, to that same volume of space taken from a more typical, average region of the universe, the void would contain somewhere between roughly a tenth and half as much material. This range holds true whether we're discussing the overall matter density, the density compared to the universe's mean, or simply how void interiors compare to cosmic averages more broadly. However it's phrased, the underlying truth remains the same. Void interiors typically carry somewhere between 10 and 50% of the density found in more typical regions of space. A significant thinning, but, as we've already discussed, rarely a total absence. 10 to 50%, though, describes an ordinary void, a fairly typical example, among the countless such regions scattered throughout the observable universe. But some voids go further. Much further. In the very deepest, most extreme examples, the density of ordinary matter can fall to more than 100 times lower than the cosmic average. Not 50% lower. Not even 90% lower. But more than 100 times lower, a level of scarcity that pushes these particular regions into an entirely different category of emptiness altogether. Some deep void regions carry so little ordinary matter that this hundredfold reduction becomes almost an understatement. If an average patch of the universe holds a certain amount of matter within a given volume, these deep voids might hold barely 1% of that amount, or even less, spread across the same volume of space. Try, gently, to hold both of these numbers in your mind at once. A typical void, thinned to somewhere between 10 and 50% of average density. And then, within that broader category, certain deep voids thinning out even further still, past the hundredfold mark, into a scarcity that borders on true nothingness, without ever quite arriving there completely. It raises a quiet, curious question, doesn't it? If ordinary voids are already so empty, what makes some voids empty themselves out even further than the rest? What determines how thoroughly a given region of space surrenders its matter to the surrounding cosmic web, rather than holding on to even the faint traces most voids retain? The answer, as with so much in cosmology, traces back to gravity, and to time. Small, almost imperceptible differences in the early universe, tiny variations in density, present from the very earliest moments after the Big Bang, determined, over billions of years, exactly how matter would eventually settle. Regions with even slightly less matter to begin with found themselves losing more of that matter over time, as gravity gradually pulled everything nearby toward denser neighboring regions instead. The rich got richer. The empty grew emptier. And across unimaginable stretches of time, small initial differences amplified into the vast contrast we observe today, between crowded filaments dense with galaxies, and deep voids where matter has thinned to a fraction of the cosmic average. There's something almost meditative in tracing that process backward, realizing that today's profound emptiness began as nothing more than the faintest, most delicate imbalance, present in the universe's very first instance. A whisper of difference, so slight it would have been undetectable at the time, patiently amplified over billions upon billions of years into the vast, quiet rooms we've been exploring together tonight. Nothing sudden. Nothing violent. Just the slow, patient unfolding of gravity, working quietly across an almost incomprehensible span of time, sorting the universe gradually into its fullest and its emptiest places alike. As we drift onward into the next part of our journey, we'll turn our attention to the galaxies that do manage to survive within these sparse, quiet interiors, the strange, isolated lives they lead, adrift far from any crowded neighborhood, and what studying them has taught astronomers about galaxy formation itself, out in the loneliest reaches of the cosmos. For now, let this settle over you gently. Vast rooms of near emptiness, some thin to half of the cosmic average, others thin past 100-fold beyond it, and, drifting quietly within them, the faintest ghostly tendrils of matter, too faint to see, too vast to fully imagine, patiently holding their place in the dark. Let's go deeper still. Into the very heart of the emptiest voids we know of, past the faint tendrils of dark matter, past even the sparse scattering of isolated galaxies, into regions so profoundly underdense that they begin to test the very limits of what empty can mean. In the deepest of these regions, something remarkable happens. Even dark matter, that mysterious substance which gathers almost everywhere else in the universe, forming faint structures even within ordinary voids, struggles to maintain a meaningful presence. The deepest void regions can be so extraordinarily underdense that not even dark matter significantly penetrates them. Think back to what we learned earlier, the faint, ghostly filaments of dark matter drifting through typical voids, forming delicate echoes of the cosmic web in miniature. In the deepest voids, even that faint echo begins to fade away. It's a kind of emptiness layered upon emptiness. First, the ordinary matter thins to almost nothing. And then, even the invisible scaffolding that usually persists in fainter form, retreats as well, leaving behind something close to true, unstructured space. To understand just how sparse this can become, it helps to move away from percentages and comparisons for a moment, and think instead in far more concrete, almost startling terms. In the emptiest parts of these voids, matter can become so sparse that a single cubic meter of space might contain only a few atoms. Pause with that thought for a moment, because it's worth truly absorbing. Think of the air around you right now, wherever you happen to be listening to this. Even in a room that feels perfectly still, perfectly empty, every cubic meter of that air is packed with an almost unimaginable number of atoms and molecules, something on the order of many billion of them, constantly in motion, constantly colliding, filling the space so densely that you never think twice about its presence. Now imagine that same volume of space, a single cubic meter, containing not billions upon billions of atoms, but only a handful. Perhaps 2. Perhaps 5. A stretch of space vast enough to hold a person, containing so little matter that it could almost be counted, one atom at a time, on your fingers. That is the kind of emptiness some regions of the deepest voids approach. And if that image doesn't quite settle in fully, here is another way of picturing the same idea, on an even more dramatic scale. Deep inside the emptiest voids, ordinary matter can become so sparse that you might find only a single hydrogen atom within a volume of space the size of an entire football field. Not a few atoms scattered here and there. A single one. One lone hydrogen atom, drifting somewhere within a volume large enough to hold a stadium crowd, a marching band, an entire game in progress, utterly, overwhelmingly alone within that space. It's hard to think of a more vivid illustration of true cosmic solitude than that. A single atom, drifting through a stretch of space large enough to contain an entire sporting event, with nothing else nearby to keep it company. No neighboring atoms close enough to interact with. No warmth. No light. Just presence, alone, in the dark. And this leads naturally to another quiet consequence of such extreme emptiness. In regions where particles are spread this thin, where collisions and interactions become almost vanishingly rare, something interesting happens to temperature itself. Very low-density regions can remain extremely cold, with the motion of individual particles slowed to something close to a near standstill. Temperature, at its most basic level, is really just a measure of how much particles are moving, how energetically they vibrate, collide, and jostle against one another. In a crowded room full of air, particles are constantly bumping into each other, exchanging energy, keeping things lively, keeping things warm. But in the emptiest reaches of a void, with almost nothing nearby to collide with, particles drift in near total isolation, their motion slowing, their energy dissipating, with nothing around to stir them back into activity. The result is a kind of profound cosmic cold, not simply the absence of heat, but something closer to stillness itself, settling over regions where matter has become too sparse to sustain much motion at all. It's a strange, quiet image to hold on to as we drift further into this exploration, vast reaches of space, so cold, so still, that individual atoms drift for eons without ever meeting another, their motion slowing gradually, like a held breath that never quite needs to be released. Alongside this cold, there is also darkness. Profound, nearly complete darkness. Some sources describe voids as being among the darkest environments the universe has to offer, and it isn't difficult to understand why. With so few galaxies, so few stars, scattered across such enormous distances, there is very little nearby light to illuminate these regions. No nearby stars casting warm light across the dark. No nearby galaxies glowing softly in the distance. Simply an overwhelming, nearly complete absence of light sources, for hundreds of millions of light years in every direction. If you could somehow stand within the depths of one of these voids and look outward in any direction, you would find, for the most part, nothing but blackness. Every so often, perhaps, the faintest smudge of distant light, some far-off galaxy so distant that its glow barely qualifies as light at all by the time it reaches you. But mostly, darkness. Complete, unbroken, and ancient. And yet, even here, in the darkest, emptiest, coldest reaches of existence, something remains. Something universal. Something that reaches into every corner of the cosmos, no matter how empty. The cosmic microwave background. This faint relic radiation, left over from the universe's earliest moments, fills every corner of space, including the deepest voids. Even the emptiest regions, thin past 100-fold below the cosmic average, cold enough to slow particle motion to a near standstill, dark enough to hold almost no visible light, are still permeated by this faint whisper of ancient radiation, dating back to the very beginning of everything. It's a remarkable thought, isn't it? No matter how far matter thins out, No matter how completely galaxies and stars and even dark matter retreat from a given region of space, this one thing remains constant. The cosmic microwave background touches every corner of the universe equally, filling even the darkest, loneliest voids with its faint, ancient glow, a glow far too faint and far too different from visible light for human eyes to ever perceive directly, but present nonetheless, everywhere, always. In a strange way, it means that even the emptiest void in the universe is never truly, completely alone. Even there, surrounded by cold and darkness and near total absence of ordinary matter, the universe's oldest light still lingers, a faint, patient reminder of the very beginning, reaching into even the furthest, quietest corners of existence. Now, let's turn our attention, gently, to the handful of galaxies that do manage to persist within these sparse and isolated regions, the void galaxies, as astronomers sometimes call them. Life, for a galaxy adrift within a void, looks quite different from life within a crowded galactic neighborhood. Some galaxies in these isolated, depleted regions have already used up whatever gas they once had, and have simply stopped forming new stars altogether. Star formation requires raw material, vast clouds of hydrogen gas, gradually collapsing under gravity to ignite new stars. But within a void, with matter already so scarce, galaxies often find themselves with very little gas remaining to draw upon. These regions, as a whole, tend to show very little star formation, precisely because there simply isn't enough gas and matter available to build new stars in any significant quantity. A galaxy that might have continued forming new stars for billions of years, had it remained within a denser, richer region of the cosmic web, instead finds itself gradually running dry, its supply of raw material never adequately replenished by its sparse, distant surroundings. It's a little like a garden planted in increasingly poor soil, with rain becoming rarer and rarer over time. At first, growth continues, perhaps a bit more slowly than before. But eventually, without fresh nourishment arriving to sustain it, that growth begins to slow, and finally, quietly, comes to a stop. And beyond simply forming fewer stars, void galaxies often behave differently from their counterparts in denser regions in other ways as well. Astronomers have found that void galaxies tend toward more isolated patterns of evolution overall, developing along paths shaped by their profound solitude, rather than through the frequent interactions, mergers, and gravitational encounters that so often influence galaxies in busier regions. Their brightness trends, too, often differ, tending to run fainter, on average, than galaxies that developed amid the richer, more crowded environments of the cosmic web. There's something quietly poignant in that idea, if you let yourself sit with it. A galaxy, adrift for billions of years in the profound isolation of a void, slowly using up whatever resources it once had, gradually dimming, gradually settling into a kind of long, patient stillness, not through any dramatic event, but simply through the slow, inevitable consequence of its solitude. No nearby galaxies to share gas with, to spark new bursts of star formation, to disturb its quiet decline. Just time, passing slowly, in the dark. As we continue onward from here, we'll explore this idea further, the specific and sometimes surprising ways that isolation itself has become an area of genuine scientific study, as astronomers work to understand exactly how a galaxy's environment, whether crowded or profoundly alone, shapes the entire course of its long and quiet life. For now, let this settle over you gently, regions so empty that a single atom might drift alone within a stadium-sized stretch of space, so cold that motion itself nearly ceases, so dark that starlight rarely reaches them at all, and yet, even there, the oldest light in the universe continues to softly, patiently, shine. We've spent quite some time now exploring the sheer scale of these places, their staggering emptiness, their strange faint structures, the isolated galaxies drifting quietly within them. Let's shift our attention, gently, toward understanding something a little different now, not simply how empty these voids are, but why they take the particular shape they do. Why they form at all, and what their internal structure actually looks like, once you move past simply calling them empty and start examining them more closely. At the heart of it all lies something we've touched on before, but which deserves a slightly closer look. Voids form naturally, as a direct consequence of gravity's patient, ongoing work throughout the universe. Gravity pulls matter together, draws it inward, gathers it into filaments, into walls, into the dense knots where galaxy clusters eventually form. And wherever matter gathers, it must, by simple necessity, leave other places behind. Emptier. Thinner. Voids are what remain in the spaces gravity chose not to fill. It's a beautifully simple idea, when you get down to it. Nothing mysterious. Nothing requiring some special, separate process just to explain the voids themselves. They arise naturally, inevitably, as the flip side of the very same process that built galaxies, clusters, and the entire grand structure of the cosmic web. Wherever there is a filament, there must also be the space the filament drew its matter away from. Wherever there is a wall of galaxies, there must be a corresponding thinning nearby, a region left emptier because its matter migrated elsewhere. Fullness and emptiness, in other words, were never separate stories. They are two expressions of exactly the same underlying process, gravity's slow, patient sculpting of matter across billions of years. Now, here's something that might surprise you a little, especially if you've been picturing voids as simple, uniform bubbles of empty space, equally thin throughout their entire volume. That picture, it turns out, isn't quite accurate. The center of a void usually holds the deepest underdensity of the entire region, not the edges, as you might intuitively expect, but the very heart of the void itself. If you were to travel from the boundary of a void inward, toward its center, the emptiness wouldn't remain constant along the way. It would actually deepen, gradually, becoming progressively more sparse the further inward you traveled, until reaching its most profound emptiness right at the center. This is worth sitting with for a moment, because it reshapes the simple image of a void as a smooth, evenly hollow bubble. Instead, void density profiles typically reveal something more nuanced, a deep, pronounced low-density center, rather than a flat, uniform emptiness spread evenly throughout. Picture it almost like a bowl, gently curving downward toward its lowest point. Except, in this case, the bowl isn't made of any physical material at all. It's simply a gradient of density, growing sparser and sparser as you move inward, reaching its thinnest, most profound emptiness precisely at the void's core. This pattern holds true across void after void, wherever astronomers have taken the time to carefully map their internal density. The deepest underdensity consistently appears near the center, rather than near the outer boundary. It's become something of a defining characteristic, a signature shape that voids tend to share, almost universally, regardless of their individual size or location within the cosmic web. Their average density profiles, taken together across many studied voids, reveal this same underlying pattern quite clearly. A pronounced dip in density right at the center. And then, moving outward from that central point, something else begins to happen, something almost the opposite of what you might expect. As you continue traveling outward from a void's empty core, approaching its outer boundary, the density doesn't just gradually return to the cosmic average and stop there. It actually rises above it. Right around the edge, matter tends to pile up somewhat, forming what astronomers call a compensation wall. This term, compensation wall, describes exactly what it sounds like. A region near the boundary of a void, where matter has gathered more densely than the universe's overall average, as if compensating, in some sense, for all the matter absent from the void's empty interior. Many voids develop this compensation wall at a fairly predictable location, roughly one void radius out from the center. In other words, if you measured the distance from the very center of a void out to its typical edge, and then continued that same distance a little further outward, you would often find this slightly denser wall of matter, marking something like a boundary between the void's emptiness and the more typical, richer regions of the cosmic web beyond it. It's a strange, elegant sort of balance, when you think about it. The universe seems to conserve matter in a fairly consistent way, at least on these very large scales. The material missing from a void's deep, empty interior doesn't simply vanish. It appears to have been redistributed, pushed gently outward over billions of years, gathering instead along the void's outer edges, forming this slightly denser wall exactly where the void's emptiness gives way to fuller, richer surroundings. Many voids develop this compensation wall in more or less the same way, matter gradually piling up around the boundary as the void's interior thins out over cosmic time. It's almost as if each void, in forming, pushed its own material gently outward, like a slow-motion ripple, leaving an empty basin at the center and a slightly raised rim along the edges. Near about one void radius out from the center, this compensation wall tends to appear, a boundary region where the density of matter climbs back up, and often even exceeds, the average density found across the broader universe. It's a subtle feature, easy to overlook amid all the larger, more dramatic facts about void sizes and emptiness, but one that reveals something rather beautiful about how thoroughly interconnected the universe's structure really is. Nothing forms in true isolation. Even the emptiest regions shape, and are shaped by, the material that surrounds them. Interestingly, this compensation effect doesn't appear equally strong across every void. There's a pattern here too, one connected to the void's overall size. Smaller voids tend to develop stronger compensation walls than their larger counterparts. In other words, the more modest, smaller voids scattered throughout the universe tend to show a more pronounced buildup of matter along their edges, compared to the truly enormous voids, like the Boötes Void, whose compensation walls tend to be comparatively fainter, more subtle, less sharply defined. There's a certain logic to this, when you consider how these structures likely formed. A smaller void represents a smaller region from which matter needed to be pushed outward, over a comparatively shorter distance, allowing that displaced material to gather more densely, more efficiently, along a nearby boundary. A larger void, by contrast, represents such an enormous, sprawling region that the matter displaced from its depths has much further to travel, spreading more thinly, more diffusely, by the time it reaches the void's much more distant edges. The compensation still happens. It's simply spread more gently, more gradually, across a much larger boundary, resulting in a subtler, less pronounced wall. There's something quietly satisfying in understanding this deeper structure, isn't there? What once seemed like simple, undifferentiated emptiness turns out to have its own quiet architecture. A deep, hollow heart at the center. A gradual thinning that intensifies as you move inward. And finally, a gentle, compensating rise in density along the outer edges, where the void's emptiness gradually surrenders to the fuller, richer cosmic web beyond. Nothing about it feels random, once you look closely enough. It feels, instead, like the natural, inevitable outcome of gravity's patient work, repeated across countless individual voids, each one shaped by the same underlying physics, each one settling, over billions of years, into this same characteristic form, hollow at the heart, and quietly rimmed with just a little more substance, right where the emptiness finally begins to end. As we move into the next stretch of our journey together, we'll turn our attention to how astronomers actually go about detecting and mapping these voids in the first place, the surveys, the techniques, and the patient decades of observation that gradually revealed just how much of the universe's true structure had been hiding in plain sight, in the vast quiet spaces between the galaxies we'd always been watching so closely. For now, let this settle over you gently, every void holding its own quiet architecture, a deep and hollow center, and, far out along its edges, the faintest gathering of matter, marking the place where profound emptiness slowly gives way, once again, to the fuller universe beyond. We left off with a quiet observation, that smaller voids tend to develop stronger, more pronounced compensation walls than their larger counterparts. It's a detail worth carrying forward with us now, because it opens the door to something even more interesting. Not just where matter gathers within and around a void, but how it got there in the first place. Which means, quite naturally, that we're about to shift our attention toward motion. Toward the slow, patient currents flowing through these vast, empty regions. Let's linger, briefly, on that first idea once more before we move forward, because it really does deserve a moment of quiet reflection. Smaller voids generally have stronger compensation walls than larger ones, a pattern confirmed again and again across careful studies of void structure. It's become one of those small, consistent truths about the cosmos, the kind of detail that keeps reappearing no matter how many different voids astronomers examine. Smaller voids simply tend to build taller, more pronounced walls of gathered matter around their edges, compared to their much larger, more sprawling cousins. There's a kind of quiet consistency in that. Nature, it seems, rarely does things halfway. Once a pattern like this establishes itself, whether through the underlying physics of gravity, or the geometry of how matter redistributes itself across a smaller versus a larger boundary, it tends to repeat itself faithfully, void after void, scattered throughout the observable universe. But walls and boundaries, as fascinating as they are, only tell part of the story. To really understand what's happening inside a void, we need to think not just about where matter sits, but about how it's actually moving. Because voids, for all their emptiness, are not still in every sense of the word. There is motion here. Slow, patient, almost imperceptibly gentle when measured against human timescales, but motion nonetheless. Matter inside voids often shows a very particular kind of movement. Near the center of a void, material tends to flow outward, gradually drifting away from the void's empty heart, moving toward its edges. And near the boundary itself, in that region where the compensation wall gathers, matter often does something rather different. It begins to fall inward, drawn toward the growing density accumulating along the edge. Picture it, gently, like a very slow exhale. Matter near the deepest, emptiest part of a void drifts outward, as if the void itself is patiently breathing its remaining material toward its own edges. And once that material approaches the boundary, where the density has already begun climbing back toward, and even past, the cosmic average, gravity takes hold a little more firmly, pulling that same material inward, drawing it toward the denser wall forming there. Outward from the center. Inward near the edge. Two different directions of movement, occurring simultaneously within the very same void, each one shaping the overall structure a little further over time. Astronomers have a specific name for that outward motion, occurring near a void center. They call it outstreaming. It's a fittingly gentle word, isn't it, for such a gentle, patient process. Matter inside voids often moves outward from the center, in this slow, continuous outstreaming, not rushing, not scattering violently, but gradually, steadily drifting away from the emptiest point, over spans of time so long they become difficult to fully appreciate. This outstreaming isn't a rare or unusual phenomenon either. It appears to be a genuinely common feature of voids in general. Matter near the center consistently tends to stream outward, while, simultaneously, matter positioned nearer the boundary tends to behave in the opposite way, falling inward instead, drawn toward the accumulating density of the compensation wall. Together, these two patterns, considered as a whole, form what astronomers describe as a void's velocity field, a way of mapping not just where matter sits within a void, but how, and in which direction, it tends to move. And time and again, across countless studied examples, that velocity field reveals the very same underlying pattern. Outstreaming near the center. Infalling motion near the outer edge. It's worth pausing here, letting this image settle fully, because there's something quietly beautiful about it. A void isn't simply a static, empty room, sitting motionless within the universe. It's closer to a slow, breathing structure, its innermost material gently drifting outward, its outer material gently drawn inward, the whole system settling, ever so slowly, into a kind of long-term equilibrium, spanning timescales far beyond anything a human mind naturally grasps. Now, you might wonder how astronomers manage to describe such subtle, almost imperceptible motion with any real precision. After all, we're not talking about winds you could feel, or currents you could watch ripple past. We're talking about matter drifting across distances of tens of millions of light years, at speeds so gentle, relative to the sheer scale involved, that this motion could never be observed directly, in any simple, visual sense. The answer lies in mathematics, specifically, in something astronomers refer to as linear mass conservation. This idea, at its heart, is really an application of a very old, very fundamental principle. Matter, on large cosmic scales, doesn't simply appear or disappear. It moves, it redistributes, it flows from one region to another, but its overall presence within the universe remains conserved, accounted for, even as its precise location shifts gradually over time. By carefully applying this principle of conservation to the observed density patterns within a void, the deep emptiness at the center, the gradual thinning as you move inward, the rising density approaching the compensation wall, astronomers are able to mathematically describe, and even predict, the underlying velocity patterns responsible for creating that density structure in the first place. These velocity patterns, in other words, aren't simply observed directly by watching individual galaxies move in real time, which would be impossible given the timescales involved. Instead, they're inferred, carefully calculated from the void's density profile itself, using this principle of linear mass conservation to work backward from where matter currently sits, toward understanding how it must have moved to get there. It's a remarkably elegant approach, when you think about it. Rather than needing to watch a void evolve directly, which would require patience spanning many millions of years far beyond any human lifetime, astronomers instead read the void's current structure like a kind of frozen record of its history. The deep emptiness at the center. The gradual gathering of matter near the edges. Each of these details, carefully measured and mapped, tells its own quiet story about the slow currents of outstreaming and infalling motion that shaped it, patiently, over unimaginable spans of cosmic time. There's something almost peaceful in recognizing that even something as vast, as empty, as seemingly still as a cosmic void, is quietly, continuously in motion. Nothing about it happens quickly. Nothing about it happens with any urgency at all. But it happens, nonetheless, matter drifting outward from the emptiest depths, gathering gradually along distant edges, the whole vast structure very slowly settling into its own patient, long-term balance. As we continue drifting forward into the segments ahead, we'll begin exploring how astronomers first learned to detect these subtle patterns at all, the surveys, the techniques, and the long, careful decades of mapping that revealed not just where voids exist, but how their quiet, internal currents continue to shape them, even now, even as we rest here tonight, listening to their story unfold. For now, let this settle over you slowly. Vast, hollow rooms, breathing ever so gently, their emptiest matter drifting outward, their edges quietly gathering what little remains, moving so slowly, so patiently, that within a single human lifetime, the motion itself would be almost impossible to detect at all. We've spent a great deal of time now exploring what voids are, how they're shaped, and how they gently move and breathe across unimaginable stretches of time. But there's another question worth sitting with, quietly, as we continue on: why any of this matters. why astronomers devote entire careers to studying regions of space defined, essentially, by their absence of things to study. The answer, as it turns out, reaches far beyond the voids themselves. Astronomers study these vast, empty regions because they help reveal something much larger: how matter is distributed across the very largest scales the universe has to offer. A void, on its own, might seem like a strange subject for serious scientific attention. But understood as one piece of a much larger puzzle, its value becomes clear rather quickly. To truly understand how the universe organized itself, how galaxies gathered into filaments and walls, how the entire cosmic web took its current shape, you need to understand not only where matter went, but just as importantly, where it didn't. Voids, in other words, are not simply empty space to be politely overlooked while astronomers focus their attention on busier, more crowded regions. They are, in their own quiet way, just as informative as the galaxies and clusters that surround them. Sometimes, perhaps, even more so. This is part of why scientists find voids so useful for testing cosmological models, the broad theoretical frameworks that attempt to describe how the universe began, how it evolved, and how it continues to change today. A cosmological model isn't simply meant to explain the crowded, busy parts of the universe. It needs to account for everything, including the vast, quiet stretches that make up most of the universe's total volume. And it turns out that voids offer a particularly sensitive way of testing whether these models hold up. Voids are useful for testing cosmological models specifically because their structure responds, quite directly, to how the universe has grown and changed over time. As the universe expands, as matter continues its slow gravitational sorting into filaments and clusters, voids don't remain static. They shift. They grow. Their internal density profiles evolve, gradually, in ways that are deeply connected to the underlying physics governing the universe's expansion. This means that by carefully studying how voids are shaped, how large they've grown, and how their internal structure compares to theoretical predictions, astronomers gain a remarkably sensitive tool for checking whether our broader understanding of the universe is accurate. If a particular cosmological model predicts one kind of void behavior, and real, observed voids consistently behave differently, that discrepancy becomes an important clue, a sign that something in the underlying model may need to be reconsidered. More broadly, voids help scientists understand how matter behaves on the largest possible scales of all, scales far beyond individual galaxies, far beyond even galaxy clusters, extending outward to the very structure of the cosmic web itself. Because voids occupy such an enormous share of the universe's total volume, understanding their behavior is, in a very real sense, understanding how the majority of cosmic space actually behaves. This extends even further, into questions of time as much as space. Scientists study voids partly because they help reveal how galaxies and matter evolve, not just across different regions, but across different eras of cosmic history as well. A void observed relatively nearby, in cosmic terms, offers a snapshot of relatively recent structure. A void observed much farther away, whose light has taken billions of years longer to reach us, offers a glimpse into how voids appeared much earlier in the universe's history. By comparing these different snapshots, Taken across vast stretches of both space and time, astronomers can begin piecing together how voids themselves evolve, how they grow, how their internal density profiles shift, how their compensation walls develop and change, across the long arc of cosmic history. Voids become, in this sense, a kind of patient historical record, written not in words, but in density, structure, and scale, waiting quietly to be read by anyone willing to study them closely enough. This makes them especially useful for studying how cosmic structure evolves, more broadly, across both time and scale, offering a complementary perspective to studies focused on galaxies and clusters, one that captures the story of the universe's emptiness alongside the more commonly studied story of its fullness. But perhaps the most intriguing reason voids draw such careful scientific attention involves some of the most mysterious open questions in all of cosmology today. Scientists use voids as what's sometimes called a cosmological probe, a tool for investigating deep, unresolved puzzles about the universe's fundamental nature. Among these puzzles are two in particular that have captured enormous scientific interest in recent years. Dark energy, the mysterious force believed to be driving the universe's accelerating expansion. And something known as the Hubble tension, a puzzling disagreement between different methods of measuring exactly how quickly the universe is expanding, a disagreement that has yet to be fully resolved. Voids, it turns out, offer a particularly useful environment for investigating both of these mysteries. And there's an elegant reason why. Scientists also study voids because they can help probe another elusive component of the universe, neutrinos, tiny, almost massless particles that interact so weakly with other matter that they can pass through entire planets without being stopped. Within the sparse, low-density environment of a void, neutrinos are able to stream freely, largely undisturbed by nearby matter, offering researchers a cleaner, more direct way of studying their behavior than would be possible in busier, more crowded regions of space. And this idea of cleaner observation applies just as powerfully, perhaps even more so, to the mystery of dark energy itself. Dark energy becomes especially important within voids, precisely because matter is so extraordinarily sparse there. In busy, matter-rich regions of the universe, the gravitational pull of nearby galaxies and clusters tends to dominate the local dynamics, making it difficult to isolate the subtle influence of dark energy from the much stronger effects of ordinary gravity. But within a void, where matter has thinned to a small fraction of the cosmic average, gravity's usual dominance fades considerably. And in that fading, something else has room to become noticeable. In fact, deep within the emptiest parts of these voids, dark energy doesn't just become easier to detect. It becomes the dominant influence altogether. Dark energy becomes the dominant component in the deepest parts of voids, precisely because ordinary matter has become so profoundly scarce there that it can no longer compete, gravitationally, with dark energy's steady, expansive influence. There's something quietly remarkable in that thought, isn't there? In the busiest, most matter-rich regions of the universe, dark energy's influence remains subtle, almost hidden beneath the far stronger, more immediate pull of nearby gravity. But travel out into the deep, quiet heart of a void, into a region so empty that a single atom might drift alone within a space the size of a football field, and something shifts. There, in that profound emptiness, dark energy finally has room to reveal itself clearly, becoming, in these deepest, loneliest regions, the single most influential force shaping how space itself continues to stretch and grow. It's a strange, quiet irony when you sit with it for a while. The emptiest places in the universe turn out to be among the very best places to study one of its greatest remaining mysteries. Places defined by absence, by scarcity, by profound isolation, becoming, almost paradoxically, some of the most scientifically valuable regions the cosmos has to offer. Perhaps there's something worth carrying forward from that thought, gently, into the rest of tonight's journey. Sometimes, the quietest places, the ones easiest to overlook, are the ones with the most to teach us, if only we take the time to listen closely enough, patiently enough, to hear what they have to say. As we drift onward into the next segment, we'll continue exploring this connection further, how the study of voids ties into humanity's broader effort to understand the universe's ultimate fate, and what these vast, quiet regions might still have left to reveal, as our tools for observing them continue to grow more precise with each passing year. For now, let this settle over you slowly. Vast, empty rooms, so sparse that gravity itself begins to lose its grip, leaving room, in that profound quiet, for one of the universe's deepest mysteries to finally step forward into view. Let's continue from where we left off, this idea that the emptiest regions of the universe might have the most to teach us. Because as it turns out, that idea reaches even further than we've explored so far. Some researchers have begun to wonder whether voids might do more than simply help us study dark energy. They may, in fact, help explain one of the deepest mysteries surrounding it in the first place. Some researchers think voids may help explain the universe's accelerated expansion without needing to invoke dark energy in quite the usual way it's typically described. This is a subtle, still developing area of cosmological thought, and it's worth approaching gently, without rushing toward any firm conclusions. The standard explanation for why the universe's expansion appears to be accelerating relies on dark energy, treated as a kind of uniform property present everywhere throughout space. But some scientists have proposed an intriguing alternative, that perhaps the observed acceleration isn't quite so uniform after all. That perhaps it emerges, at least in part, from the uneven distribution of matter throughout the universe itself, from the very structure of filaments, walls, and voids we've spent so much time exploring together. In this view, the profound emptiness of voids, sitting alongside the crowded density of filaments and clusters, might itself be contributing to how we perceive and measure the universe's expansion, without necessarily requiring a separate, mysterious form of energy to explain the effect entirely on its own. It's an idea still being carefully tested and debated, one among several competing explanations that researchers continue to investigate. But it speaks, once again, to just how central these vast, quiet regions have become to some of the biggest open questions in modern cosmology. One of the more remarkable tools astronomers have developed for studying voids more directly involves something called weak gravitational lensing. This technique relies on a strange and rather beautiful consequence of how gravity interacts with light itself. Massive objects, according to general relativity, bend the path of light passing near them ever so slightly. And this means that light traveling toward us from extremely distant galaxies, passing through or near a void along its journey, will be subtly affected by however much or however little mass that void actually contains. Some voids are now studied using precisely this technique, allowing astronomers to estimate how much mass is genuinely missing from within them, based on how gently, or how strongly, that missing mass fails to bend the light passing through. It's an elegant, indirect method, using the faint, careful measurement of distant starlight to essentially weigh the emptiness of a void, without ever needing to observe the void's sparse contents directly at all. Voids serve another important purpose in cosmology as well, one connected to a foundational assumption that underlies much of how scientists think about the universe's overall structure. This assumption is known as the cosmological principle, the idea that, on sufficiently large scales, the universe should appear roughly uniform and the same in every direction, without any special or privileged locations. Void research can help test whether this cosmological principle genuinely continues to hold true, even at the very largest scales we're capable of observing. If voids, filaments, and walls were distributed in some unusual, unexpected pattern, inconsistent with what the cosmological principle would predict, that discrepancy could suggest something profound, perhaps an oversight in our current understanding of how the universe's largest structures actually form and behave. So far, studies of voids have generally supported this foundational assumption, but the careful, ongoing work of testing it continues, void by void, survey by survey. Interestingly, voids also play a quieter, more practical role in refining how astronomers measure cosmic distances altogether. Some voids are used specifically to improve these distance measurements, because local underdensities, like the ones found within voids, can subtly affect how the universe's expansion is inferred from nearby observations. Without carefully accounting for the presence of these void regions, distance measurements taken from surveys of relatively nearby galaxies could end up slightly skewed, subtly distorted by the local variations in density scattered throughout our own cosmic neighborhood. By understanding the voids nearby, astronomers can correct for these effects, arriving at cleaner, more accurate distance measurements across the wider universe. This connects to something else quite fascinating that recent research has begun to reveal. Some large structures found relatively nearby in cosmic terms may be shaped less by simple, uniform cosmic expansion, and more by the surrounding voids and sheets of matter positioned around them. In other words, the particular shape and movement of certain nearby structures might owe less to the universe's broad, general expansion, and more to the specific, local influence of the voids and denser sheets sitting immediately alongside them, a reminder that even on relatively nearby scales, the fine details of cosmic structure matter enormously in shaping what we ultimately observe. There's also a quiet, ongoing story revealed through studying how voids themselves have changed across cosmic time. Recent studies suggest that voids become progressively emptier as the universe ages, with the sparse galaxy populations scattered throughout them growing dimmer and less tightly clustered as we move closer toward the present day. It's a slow, patient trend, unfolding across billions of years, voids growing gradually emptier, their scattered galaxies fading and drifting further apart from one another, as the underlying process of cosmic expansion and gravitational sorting continues its steady, unhurried work. Of course, none of this would be possible without first successfully identifying where these vast, empty regions actually exist throughout the observable universe. And that task, it turns out, has its own long and interesting history. Astronomers have identified extraordinarily large empty regions scattered throughout the cosmic web using modern galaxy surveys, alongside sophisticated techniques for mapping the distribution of dark matter across large volumes of space. These surveys involve carefully cataloging the positions of enormous numbers of galaxies, building up, gradually, an increasingly detailed three-dimensional map of how matter is truly distributed throughout the observable universe, a map within which voids naturally reveal themselves, as the vast empty regions between the mapped concentrations of galaxies elsewhere. It might seem, given how central voids have become to modern cosmology, that they would have received serious scientific attention from the very earliest days of large-scale cosmic surveys. But that wasn't entirely the case. Voids were, for quite some time, considerably underused within quantitative cosmology, largely because early researchers lacked good, objective tools for reliably identifying them in the first place. It's a reminder that scientific progress often depends not just on curiosity, but on developing the right instruments and methods to properly study a given phenomenon. Voids, by their very nature, are difficult to define with total precision. Where exactly does a void begin, and where does it end? How empty must a region become before it qualifies as a true void, rather than simply an ordinary, modestly underpopulated patch of space? Early astronomers, working with less sophisticated tools and less complete galaxy surveys, struggled to answer these questions with the kind of rigor and consistency that serious quantitative research requires. Over time, however, as galaxy surveys grew larger and more detailed, and as more sophisticated statistical methods were developed for objectively identifying and measuring void boundaries, this challenge was gradually overcome. Today, voids can be reliably identified across a wide range of research contexts. Voids can be identified in both simulations and observations alike, including detailed studies of dark matter structure, as well as careful analyses of how visible galaxies happen to be distributed throughout large volumes of space. This dual approach, drawing on both computer simulations and real observational surveys, has proven especially valuable. Voids can be studied thoroughly within computer simulations, where researchers can model the universe's evolution across billions of simulated years, tracking exactly how voids form, grow, and develop their characteristic internal structure over time. And these same voids can also be studied directly within real galaxy surveys, comparing the actual, observed universe against what these simulations predict, checking, patiently, whether theory and observation continue to align. Together, these two approaches, simulation and observation working hand in hand, have transformed voids from a once overlooked curiosity into one of the more carefully studied, and scientifically valuable, features of the entire cosmic landscape. What began as regions too difficult to properly define, too empty to seem scientifically interesting, gradually revealed themselves to be windows into some of the deepest, most fundamental questions cosmology has yet to fully answer. As we move into the next part of our journey together, we'll turn our attention towards some of the specific voids that have captured particular scientific interest over the years, their individual stories, their discoveries, and the quiet mysteries that still surround certain corners of the cosmic web, even after decades of careful, patient study. For now, let this settle over you gently. Vast, empty regions, once too difficult to properly measure, revealed patiently over decades to be quiet keepers of some of the universe's deepest secrets, still slowly emptying, still slowly dimming, as the long, unhurried story of cosmic time continues to unfold. We've traveled a long way together tonight, through vast, empty rooms stretching hundreds of millions of light years, through the strange physics of matter thinning past 100-fold below the cosmic average, through the patient outstreaming of matter near a void's hollow heart, and the quiet gathering of compensation walls along its edges. And now, as we settle into this final stretch of our journey, something rather personal awaits us. A discovery that brings this entire exploration home, quite literally. Everything we've discussed so far has, in some sense, kept these voids at arm's length. Distant regions, observed carefully, studied from afar. But there's a quieter, more intimate possibility that deserves our attention now. The Milky Way, our own galaxy, the very place we call home, may itself sit within a vast, underdense region of space. This region has a name. Astronomers call it the KBC void, though it's also known, perhaps more evocatively, as the local hole. Named after the researchers who helped identify it, the KBC void appears to be a substantial, if not especially extreme, underdense region, one that may include our entire galaxy, along with many of our nearest galactic neighbors, within its broader boundaries. Take a moment with that thought, because it reframes something rather significant about our place in the universe. We've spent this entire journey imagining voids as distant curiosities, places far removed from our own cosmic neighborhood, defined by their emptiness precisely because so little, including us, seems to exist within them. And yet here, quietly, is the suggestion that we ourselves might be residents of just such a region, not at its most extreme, hollow center, but somewhere within its broader, gently underdense reaches nonetheless. It's worth being careful here, and gentle with the uncertainty involved. Newer analyses suggest that the Milky Way may indeed sit within a broader low-density environment than astronomers once assumed, but this remains an active, ongoing area of research, still being refined and debated as new data continues to arrive. Not a settled certainty, but a genuinely compelling possibility, one that continues to gather support, little by little, as our surveys of the surrounding universe grow more precise. If true, it means that the crowded feeling of our own galactic neighborhood, filled as it seems with numerous nearby galaxies, spiral arms, and busy stellar activity, is itself set against a broader backdrop of relative emptiness, extending outward around us in every direction. A quiet home, nestled within an even quieter region, itself just one part of the vast, underdense architecture we've spent this journey exploring. There's another thread connected to this idea, one that reaches even further outward, toward one of the more curious puzzles in modern cosmology. The Eridanus Supervoid, a separate, distant region of profound emptiness, has been linked, in some studies, to something called the cosmic microwave background cold spot, an unusually cold patch found within that faint, ancient relic radiation we discussed earlier, the light left over from the universe's very earliest moments. This connection makes a certain intuitive sense, once you consider how a void's emptiness might interact with light passing through it. A low-density region can genuinely affect the temperature of the cosmic microwave background as it passes through, making certain parts of the sky appear very slightly colder than the surrounding average. As this ancient light travels across billions of years, passing through regions of varying density along its journey, it may pick up subtle imprints from the material, or lack of material, it encounters along the way. A particularly large, particularly deep void, like the Eridanus Supervoid, could conceivably leave just such an imprint, a faint, cold whisper marking its presence within light far older than the void itself. It's a delicate, still debated connection, and not one that every researcher agrees on entirely. But it speaks to something we've touched on throughout this entire journey: how deeply interconnected even the emptiest regions remain with the rest of the universe. A void doesn't simply exist in isolation. It shapes the light passing through it, however subtly. It leaves its mark, faint but real, on structures far beyond its own boundaries. This leads us, gently, toward one of the more open, unresolved questions still surrounding these vast regions. Scientists continue to debate whether the largest, most extreme void-like structures we've observed represent nothing more than rare, unusual statistical fluctuations, occasional extreme outcomes that, while striking, remain fully consistent with our current understanding of how the universe formed and evolved. Or whether, instead, these extreme structures might be hinting at something more significant, genuine clues pointing toward new physics, aspects of cosmology not yet fully captured within our existing models and theories. This question remains genuinely unresolved, and that's a worthwhile note to end on, in its own quiet way. Not every mystery explored throughout tonight's journey has been fully solved. Some remain open, actively debated, patiently awaiting further data, further study, further careful thought from researchers continuing this work even now. The universe, it seems, still holds on to some of its secrets, even within regions defined, on the surface, by their profound emptiness. And perhaps that's fitting, in its own way. We began this journey by learning that voids are not simply nothing, that they hold faint structure, subtle motion, ancient light, and quiet mathematical elegance, once you take the time to look closely enough. It seems only right that they should also hold on to a few genuine mysteries as well, questions still waiting for answers we don't yet fully have. So, why does any of this matter, in the end? Why have we spent this long, quiet journey exploring regions defined so thoroughly by their absence of things? Astronomers study these vast, empty regions because they help reveal how matter is distributed across the very largest scales the universe has to offer, a truth we return to more than once throughout tonight's exploration, because it really does sit at the heart of everything we've discussed. To understand the universe fully, you cannot simply study its crowded, busy places. You must also understand its quiet ones, its empty ones, its lonely ones. Scientists continue exploring these vast, empty regions because they offer one of the clearest windows we have into the broader evolution of the entire cosmos. Not despite their emptiness, but because of it. In the hush of these regions, away from the overwhelming gravitational influence of crowded galaxies and clusters, subtler truths become visible, The quiet influence of dark energy, the delicate passage of neutrinos, the patient testing of our deepest cosmological assumptions. And so, perhaps, we arrive at the quiet thought this entire journey has been gently building toward, from its very first moment. In a universe filled with billions upon billions of galaxies, scattered across an almost incomprehensible expanse of space and time, it may ultimately be the loneliest places, the vast, hollow, quiet voids, that teach us the most about how everything truly came to be. There's something worth sitting within that, as we bring tonight's journey to its gentle close. We so often measure significance by presence, by fullness, by brightness, and activity, and crowded abundance. And yet, across this exploration, we've seen again and again how the opposite can be equally true. How absence itself can carry deep meaning. How emptiness, studied patiently and carefully enough, can reveal truths that fullness alone would never show us. Perhaps there's something quietly reassuring in that thought too, if you let it settle all the way down into whatever quiet corner of your own mind still happens to be listening. That stillness has value. That solitude, even on the grandest cosmic scale, is not simply empty of meaning. That the quietest places, the least crowded, the most overlooked, may still be holding on to some of the deepest truths of all, waiting patiently, as they have for billions of years, for someone willing to listen closely enough to hear them. The universe stretches on, vast and mostly empty, filaments and walls tracing their slow gravitational patterns against an overwhelming backdrop of quiet, hollow space. Somewhere within that vastness, our own small galaxy drifts, itself resting, perhaps, within its own gentle pocket of relative emptiness, one quiet corner among countless others, adrift in the dark, held together by light that has been traveling, patiently, since the very beginning of everything. And here, at the end of this long, slow journey through the loneliest places the universe has to offer, perhaps all that remains is to rest in that vastness a while longer. To let the scale of it settle, fully and gently, without needing to hold on to every number, every name, every careful measurement we've traced together tonight. Just the quiet. Just the dark. Just the patient, ancient light, still drifting outward, still reaching us, even now, even here. Rest well.